Let's say we have the equation the absolute value of x plus 2 minus x equals 3. Before we start, we have to make sure that the absolute value stands alone by itself on one side of the equation. How do we do that? We can add x on both sides. Minus x plus x is 0. So we don't need to write the 0, because the absolute value minus 0 is still just the absolute value. Make sure that you always start like this when you have an absolute value. The best is to isolate it on the left side of your equation. There are two expressions inside the absolute value bars that are equal to x plus 2. 3 plus x and the negative of 3 plus x. Let's check that. The absolute value of 3 plus x is 3 plus x. Is this correct? Yes, it is. The absolute value of the negative of 3 plus x is 3 plus x. Is this correct? Yes, it is. So we can say x plus 2 is equal to 3 plus x. And x plus 2 is equal to negative 3 plus x. Starting with the first equation, we subtract x on both sides. And we get 2 equals 3. That's wrong. This means we have no solution in this equation. Let's look at our second equation and remove the negative sign with the parentheses. That's very easy. We just have to flip the signs in front of the x and the 3, which then looks like x plus 2 is equal to negative 3 minus x. After adding x on both sides, we get 2x plus 2 is equal to negative 3. Subtract 2 on both sides leads us to 2x is equal to negative 5. Divide by 2. X is equal to negative 5/2. Finally, we have a solution and can put it in the solution set. Let's graph the two expressions to the left and to the right of the equal sign and see if the intersection of the two graphs represent our solution negative 5/2. Hopefully that's the case. Let's graph the two expressions to the left and to the right of the equal sign and see if the intersection of the two graphs represents our solution negative 5/2. One way to draw the graphs is to know that x plus 2 represents a straight line with an intersection with the y-axis at 2, and a positive slope of 1. We also have to know that the absolute value of x plus 2 can never be negative, so we mirror the straight line at the vertical line at negative 2. Another way is just to make a table in your mind or paper. Put some x values and the y values. For x negative 1, we got 1 for y. For x negative 2, we got 0 for y, and so on. Let's do the same with the other graph of the expression x plus 3. If x is 0, 0 plus 3 is 3, so we are here. If x is 1, 1 plus 3 is 4. Here we have another point. If x is negative 2, 3 minus 2 is 1. We see that we have an intersection at negative 5/2, which is negative 2.5. And exactly our solution, which we found out with algebraic calculations. Let's look at the next example. We can do this the same way as the previous example, but let's do it a more general way to learn something new. By the way, the approach of the other example is also like this, but you can't see it at the first sight. The following approach is more detailed, which is great to see the background. If you have absolute values, you always have two cases. So we can say we solve this equation by cases. The expression between the absolute value bars can be greater than or equal 0 and less than 0. Why? Feel free to think about it and write the answer in the comments. The first case is x plus 3 is greater than or equal 0. We see after subtracting 3 on both sides that x is greater than or equal negative 3. In other words, the expression inside the absolute value bars is greater than or equal 0 only when x is greater than or equal negative 3. The second case is x plus 3 is less than 0. We see after subtracting 3 on both sides that x is less than negative 3. In other words, the expression inside the absolute value bars is less than 0 only when x is less than negative 3. Let's move on with the first case. In this case, as we see the expression between the absolute value bars, x plus 3 is greater than or equal 0. This means we can remove the absolute value bars. Do you know why? Feel free to write it in the comments. So after removing the absolute value bars, our equation looks like this. After adding x on both sides, we get 2x plus 3 equals negative 3. Subtract 3. divide by 2. Two divided by 2 is 1. We don't need to write the 1 because 1 times x is x. Negative 6 divided by 2 equals negative 3. Now we have to check if this is a real solution which we can put in our solution set. How do we do that? We do that by checking if x equals negative 3 matches with our condition that x has to be greater than or equal negative 3, because our case is valid only for x greater than or equal negative 3. Is negative 3 greater than or equal to negative 3? Yes, it is. So we have our first solution. Let's look at our second case. In this case, the expression between the absolute value bars x plus 3 is less than 0, which means we can remove the absolute value bars, but have to put parentheses around the expression with a negative sign in front. Do you know why? Feel free to write your answer in the comments. Let's remove the negative sign and the parentheses, but be careful. By doing that, flip the signs in front of the x and 3. So we have negative x minus 3 is equal to negative x minus 3. This means we have infinite solutions, but we have to check under what kind of condition. This case is for x less than negative 3. So we have infinite solutions only when x is less than negative 3. Let's put this solution and the solution from the first case together in the solution set. Negative 3 is a solution, and numbers less than negative 3 are solutions. Hence, the solution set includes all values of x such that x is less than or equal to negative 3. How would we graph this? Feel free to pause the video and try it by yourself. That's a good exercise. Let's look again at our graph to understand better. The absolute value of x plus 3 is the same graph like in the previous example. So this graph looks like this. We see that to the right of negative 3, we have no intersection with the two graphs, which means we have no solution to the right of negative 3. That's what we also found out algebraically with our calculation. But look to the left of -3. We have, let me call that infinite intersections, because the green graph covers the white graph. This also matches with our calculations that we have solutions for all values of x which are less than or equal 3. Let's move on to the next example where we have a fraction between the absolute value bars. The first step when dealing with rational expressions is to determine the domain. What's that? The domain is a set of all x accepted by our fraction. Is a 1 accepted by our fraction? 1 plus 1 equals 2. Nothing wrong with that when the denominator is 2. Is a 2 accepted? 2 plus 1 equals 3. That's also okay. What about when we choose 0 for x? 0 plus 1 equals 1. No problem. Is it possible that we can put all numbers for x? Wait, what about -1? -1 plus 1 equals 0. Can we divide by 0? Unfortunately, we cannot. Dividing by 0 is not defined, which means mathematicians didn't define what dividing by 0 is. If we would solve the equation and get later -1 as a solution, we have to discard the -1. So our domain is okay for all real numbers except the -1. Let's start again with removing the absolute value bars by focusing on the two cases. First case, x minus 2 divided by x plus 1 is greater than or equal to 0. This is our condition which we have to check later with our solution. Now we can remove the absolute value bars from our equation and solve for x. Why can we remove the absolute value bars? Because we are in the case where the expression inside the absolute value bars is greater than or equal to 0. Remember, if the thing inside the absolute value bars is greater than or equal to 0 and we remove the absolute value bars, nothing changes, because the only job for the absolute value bars is to make the expression inside the absolute value bars positive. And if the thing between the absolute value bars is already positive, we don't need the absolute value bars. To remove the denominator, we multiply by x plus 1 on both sides. And we get x minus 2 is equal to 3 times x plus 1. Let's remove the parentheses using the distributive property by multiplying 3 with x and with 1. Subtracting x on both sides leads us to -2 is equal to 2x plus 3. Subtracting 3 on both sides and we get -5 is equal to 2x. Dividing by 2, and we have x is equal to -5/2. One thing we have to check now is if negative 5/2 is allowed in our domain. Yes, it is. The only number which is not allowed is negative 1. The other thing we have to do is plug the negative 5/2 in our condition and see if that's true. So let's plug negative 5/2 instead of x in the fraction. Let's focus first on the expression on the top. The 2 is the same as 2 over 1. This helps us to find the common denominator better. In other words, we need the least common multiple of 2 and 1, which is 2. So we have negative 5/2 minus 4/2. Why 4/2? Because 4/2 is the same as 2. Always check that when you're a beginner. Let's focus on the expression at the bottom. Similarly, like before, 1 is the same as 1 over 1. So we have negative 5/2 plus 1 over 1, which is the same as 2 over 2. Now we can add the fractions. How do we do that? Add the top number and put the answer over the same denominator. Negative 5 minus 4 is negative 9. Make sure that you put the denominator only once. Let's do the same with the bottom expression. Negative 5 plus 2 is equal to negative 3. How do we divide fractions? Just write the first fraction and multiply it by the reciprocal of the second fraction. Which means reverse the numerator and the denominator of the second fraction. Negative 9/2 multiplied by negative 2/3. The 2 can be cancelled out because 2 divided by 2 is 1. And negative times negative is positive. So we have 9/3, which is 3. What did we want to check here? We wanted to check if this is greater than or equal to 0. And indeed, 3 is greater than or equal to 0, so we can put negative 5/2 in our solution set. Let's move on to the second case. X minus 2 divided by x plus 1 is less than 0. Now we can again remove the absolute value bars from our equation, but in this case we have to put parentheses around the expression in the absolute value bars and a negative sign in front. Let's remove the negative sign and the parentheses and flip the signs in front of the x and the 2. So we have negative x plus 2 divided by x plus 1 equals 3. To get rid of the denominator, we multiply the equation by x plus 1. After cancelling out x plus 1, we have negative x plus 2 is equal to 3x plus 3. Adding x on both sides gives us 2 is equal to 4x plus 3. Subtract 3 on both sides and we get negative 1 is equal to 4x. Divide by 4 and we get x is equal to negative 1/4. Now we have to check again if negative 1/4 is allowed in our domain. Yes, it is. Similarly, like in case 1, we have to plug the negative 1/4 in our condition and see if that's true, which means less than 0. So let's plug negative 1/4 into x minus 2 divided by x plus 1. Feel free to pause the video and try it by yourself. That's a good exercise. Let me do it quickly without words. And indeed, negative 3 is less than 0. So we can put negative 1/4 also in our solution set. So let's plot the graph to visualize our solutions. Feel free to pause the video and try it by yourself. We have two graphs again. One is the expression to the left of the equal sign, and one graph is the 3. The 3 is easy. It's just a horizontal line which intersects the y-axis at 3. For the other expression, we can make a quick table. By the way, we don't need the negative part of the y-axis. Why not? Feel free to write your answer in the comments. Let me quick do the table. Negative 4 minus 2 is negative 6 divided by negative 3 is 2. Negative 3 minus negative 2 divided by negative 2 is 5/2, which is 2.5. Negative 2 minus negative 2 is negative 4 divided by negative 1 is 4. Negative 1, negative 2. Negative 1 minus 2 is negative 3 divided by 0. Oh, the negative 1 is not allowed. We have to discard that. We see that here. 0 minus 2 is negative 2 divided by 1 is negative 2. 1 minus 2 is minus 1 divided by 2 is negative 1/2. 2 minus 2 is 0. 3 minus 2 is 1 divided by 4 is 1/4. Okay, let's see. Negative 4, 2, negative 3, 2.5, negative 2, 4, 0, oh, we have to do the absolute value. The absolute value is here. So, here, here, and here. So it's not negative 2. It's positive 2. It's here. 1 is 1/2. 2 is 0. And 3 is 1/4. We see that the intersections match with our algebraic calculations. Negative 5/2 is negative 2.5 and negative 1/4 is the same as negative 0.05. If you have any questions, feel free to ask me in the comments. Thanks for watching. This video is what I did for you. If you want to do something for me, hit the bell button, share and subscribe. Happy learning, everyone.